we see that these two graphs are above each other. The linear graph is the one that's higher up. The quadratic is the one below. So we're going to do top minus bottom here. So here. We can draw a representative rectangle. And we see the top of the rectangle is touching the line. The bottom of the rectangle is touching the curve. So that's how we were able to name the top graph and bottom graph. Okay. Our bounds is going to go from -2 to 2. We can also find those boundaries by setting the equations equal to each other to find those intersecting points. Bring everything over to one side. And we get x plus 2, x minus 2. Okay, top graph minus bottom graph. Top graph is the 2x plus 5. The bottom graph is the x squared plus 2x plus 1. And then our bounds is from -2 to 2. You see how everything's in terms of x here? Okay, so if we do top minus bottom, everything that we see in our definite integral should show up in terms of x. -2 to +2. That just tells us we're stacking these vertical rectangles from -2 all the way over to +2. Top graph is the line. And I think it's always a good habit to build is that whenever you're doing the bottom graph or the left graph, whatever comes after the minus sign, I think it's always a good idea to protect it with a set of parentheses so we don't forget that the negative is going to influence everything that comes after it. If you forget that set of parentheses, it's not going to matter if there's only one term, but if there are multiple terms, that's going to throw your answer off. Okay, practice entering into your calculator here. I mean, we could do this with power rule, but we're going to just transition over to using our calculator as our problems become more and more involved. So math 9, take you to your definite integral or the definite integral notation on your 36 Pro. Guys, we're going to need our calculators every day, so please try to bring it. We're going to need it, and you get to use it on the test as well. Okay, any questions with 2? Okay. I want to explore number 4, but I want to do it twice, okay? I want to do, because number 4 is one of those problems where we can do it either top minus bottom or right minus left. Not every circumstance allows for us to flip-flop between the two, but I think it's good to begin to kind of get into that mindset of looking to see, wait, can I do this top minus bottom? If not, then I've got to explore right minus left. But right minus left is more challenging because it takes more setup to get it ready for right minus left. So, we're going to skip number 3, so let's cross off number 3, but we're going to do number 4 twice, okay? So let's use this space for number 4. Let's do number 4. Let's do top minus bottom for number 4. Okay, we have 2 curves here. The curve below is the x cubed. and the curve above is the x squared. The x squared does grow at a slower rate, but between 0 and 1, it's the x squared that is going to be the faster rate one. Sorry, I didn't give a lot of room here. Okay, so we have that shaded region here, top minus bottom. We can draw these, draw a representative vertical rectangle. Top graph is the x squared, and the bottom graph is the x cubed. So we can do top minus bottom. Our bounds is from 0 to 1, the x values. Okay, top minus bottom, x squared minus x cubed. We're just following the formula above. Okay, we can work this out by hand, or you can enter in your calculator. Okay, 1/3 minus 1/4 gives us 1/12. If you enter in the calculator, you may get a decimal value. That's also acceptable. Okay, so let's look at number 4 from the other perspective of right minus left. Let me show the formula for right minus left. Now, right minus left requires some adjustments because our equation is no longer in terms of x. Our bounds are no longer in terms of x as well. So I'm going to just use function notation here. It'll be something like f of y minus g of y. So that just indicates that everything we use has to be in terms of y, which means that our equations has to be rewritten in a different form. They have to, instead of y equals and all the x's on the right side, there's going to be x equals and all the y's on the right side. So how can I rewrite the equation to get it in the proper form? Let's start with y equals x squared. X equals square root of y, right? And that's going to be y1. That's going to be the graph here. Y equals x cubed. If I want to solve for x, x equals, I take the what? The cube root, right? So the reason that we can do this right minus left is because if you can draw a horizontal rectangle, the horizontal rectangle can be consistent all the way from below to the top, right? So right minus left. Let me see if I can get this a little bit larger here. So instead of adding lining up all these vertical rectangles, we're stacking these horizontal rectangles from the bottom to the top. So the graph on the right here is the x equals cube root of y. The graph on the left here is x equals square root of y. And our bounds have to be in terms of y as well. So let's look at the order pair. The order pair here is 0, 0. And the order pair here is 1, 1. Okay, I know it feels like we're doing the same bounds as before, but we really have to just understand that if we do right minus left, we have to pick out the y values of those intersecting points. Okay, so we set it up, right minus left. Area is a depth integral from lower bound to upper bound, from the lower to the higher y value. And then right minus left. So the graph on the right, we've adjusted it. They're both in a proper form. Cube root of y is the one on the right. Square root of y is the one on the left. And then we can do power rule, but we're going to make the calculator do the work for us. Now, when you enter into the calculator, you're writing on paper in terms of y, but your calculator will always do in terms of x. Okay, so don't try to change the variable in the calculator to match what you see on paper. Always use x for your calculator. Okay, so enter that in. We should get the same answer. Okay, we're dealing with the same region, just a different orientation. If you want to get the cube root, you do math 4. Math 4 will take you to cube root. .0833. Okay, so this is what we're going to explore today. We're going to explore functions or graphs that are able to be flip-flopped and just kind of getting used to moving back and forth. Now, when we move into certain problems, you're going to decide, right, which one is better, top minus bottom or right minus left. But right now, I'm going to pick problems that can allow us to do both ways. So we kind of just see the relationship and understand that, you know, we could potentially, some problems we can potentially do both ways just to get that practice in. Okay, any questions so far? Good. All right, so let's flip over to page 5 here. This is a older free response question, but what I did was I took one problem and I kind of split it into 4 parts so that we can kind of really explore that relationship between either top minus bottom or right minus left, and also getting used to the calculator and making the calculator find some of the information that we need for us. Sorry, page 7. Okay, let me read the instructions here. It says, let R and S be the regions in the first quadrant. So first of all, it's the same picture. I just copied it 4 times. We're going to do 4 different problems from different perspectives here. R and S be the regions in the first quadrant shown in the figure. Region R is bounded by the x-axis, the graph 2 minus x cubed, and y equals tangent x. So bounded just means that it's enclosed with those graphs as the boundaries. Region S is bounded by the x-axis, sorry, the y-axis, the graph y equals 2 minus x cubed, and tangent of x. Okay, let's start with the easier one, and we'll kind of move our way down. Find the area of S. So here's S. Let's lightly shaded so we know exactly what we're working with. We want to find the area of that region. This is a nice top minus bottom because we see one graph is always consistently above the other graph. There's no need to split up into separate integrals here. So just draw a representative rectangle and just visualize moving that rectangle from one end to the other, right? If you move from one end to the other, you can kind of imagine that the top of that rectangle is always touching the same curve, and the bottom of the rectangles is always touching the same graph as well. So you get that consistency, you know that there's no sudden change. Okay, if there's a sudden change, then we need to consider that we may need multiple integrals to get that relationship to stand. So let me identify the top graph here. So the top graph is the 2 minus x cubed, right? And the bottom graph is that y equals tangent of x. Okay, so everything seems pretty straightforward, but there is a piece of information that we're missing. Okay, we have the left bound, which is what? What's the left bound of our interval? 0. But the right bound, we don't know where that is. Okay, we're going to need our calculator to help find that for us. So I'm going to do it using the graphing and the 36 Pro. So let's go to y equals. We're going to graph it. I'm going to help you practice entering this in your calculator and seeing it a little better. So if you can go to y equals. Okay. If you're using your scientific calculator, just hold on a second. I'm going to walk you through finding that intersection for you. But under y1 and y2, I have tangent x and 2 minus x cubed. It doesn't matter which one you put first. Make sure that you are in radian mode. Okay, we're dealing with trig here, okay, and we're pretty much always going to be in radian mode. Okay, we're hardly ever going to be in degree mode. Okay, any questions so far? Okay, next up, you're going to go to Zoom and do Zoom 6. Zoom 6 will give you a standard window. It may not get you where you want to be, but at least it kind of gets you a starting point. It gives you a, so do Zoom 6. Okay, we're zoomed out way too far, but we kind of have an idea where to target, right? We know that we want to get a better view of that region there. So what we're going to do now is you're going to go to Zoom and you're going to choose Zoom box. So we're going to do a Zoom box is you're going to draw a box around the region that you care to look at more closely. Hit enter. Okay, there's a cursor, but you're going to move the cursor to where you think is the upper corner of your region. Okay. Hit enter once. Okay, and don't hit enter again until you see the box in front of you. So you're going to use your directional arrows, and you're going to draw the box. Okay, don't hit enter yet until you see the full box in front of you. So I can drag it left and right, and then drag it up and down, and you can kind of see where that box is forming. Okay, now you hit enter again. Okay, and you should see a much clearer picture of what we are wanting to work with. Okay, any questions? Anybody have any issues with their graphing calculator trying to get that to show up? Okay, so what we're concerned about right now is we're trying to find that intersecting point. So what you're going to do is you're going to go to second trace intersect. I have it on the board there. So second trace intersect. It's that fifth option there, second trace intersect. So we're going to ask the calculator to find the intersecting point between two curves. Hit enter again. First curve, you're going to go to close to the source of the intersection, but you're not going to go directly on the intersection. Just get close enough so the calculator knows that you're looking for that intersecting point. And hit enter. And the cursor should jump to the other curve now. You can go left and right to make sure you're on that curve. Again, don't go to the intersection, just get close to it, hit enter again. And now the calculator is going to find the closest intersection between those 2 points that you gave it. Enter again, there's your intersection, 0.902, 1.266, okay? So we don't need the y value right now, but we're going to put the full order pair because we're going to need it later. Okay. Any questions with the graphing calculator before I move on to the 36 Pro? Everybody good with getting to that intersecting point? Now, the 36 Pro is going to help us get to this X value. Okay, it's not going to get us a Y value, but we can talk about that in a second. So on your 36 Pro, what you're going to do is you're going to go to this feature that you have called numsolve. Okay, see that numsolve. So you do second sign, will take you to numsolve. And you're going to enter both equations and set them equal to each other so they can find that intersecting point. So you'll do 2 minus x cubed. Again, make sure that you're in radian mode, that you're not in degree mode here. So you're going to do 2 minus x cubed equals tangent x. Usually I like to start at 0. It really doesn't matter here, but I'm going to just start at 0, make the calculator start there and look for the intersecting point. Okay, hit enter, enter, and this should get you to that x value for us. Good, 0.90215. So you should be able to get that 0.902. Now the y value isn't showing, but you can just find that y value by entering the 0.902 either into the x of the tangent x or the x of the 2 minus x cubed, and then you can just take that extra step to find that y value. Either function, it's the intersecting point of both graphs, so you can find that y value just by entering in. So the Scientific Pro or 36 Pro requires an extra step, but you can find what you need. Okay, so we know all we need is one integral to help us get to the area formula. We're using the x values, right? So we're going to go from left to right. Now we know that we're targeting the x values, so we're only going to use the 0 and the 0.902. So here's our area formula. Depth integral from 0 to 0.902. Top graph minus bottom graph. Okay. Again, I like to protect my bottom function with a set of parentheses. In this case, it's not really going to matter, but I just want us to build that habit of always thinking, oh, I got to worry about that negative sign that may influence everything that comes after it. Okay, the rest into your calculator. Math 9 for your 36 Pro, and then second E for your, Math 9 for TI-84, and then second E for your 36 Pro. Okay, you should get 1.161. Okay, any questions with part 1?
I got 1.6.
Yeah, let's see here. Oh yeah, go make sure you're in radian mode. Make sure that we're in radian mode. I know it's sometimes the calculator kind of flips back and forth, so always double check radian mode. Okay, so here, the second, we're also going to do find region of S. So highlight that lightly. But this is going to feel more difficult, but it's good to kind of get that practice in with right minus left. So that means that we're not going to be adding vertical rectangles to get to that region. We're going to add horizontal rectangles. Okay, if I'm going to draw a representative rectangle, then I want you to tell me if I slide that rectangle up or down, am I always hitting the same graph, the left side or the right side? Okay, anything different here? Okay, what do you notice about the right side of the rectangle? Is it all? Yeah, it switches, right? It switches. If it's up here, it's touching the 2 minus x cubed, but if it's down here, it's touching a different graph. So what does that tell us? Yeah, we need two separate, we need to think that's two separate regions. We're not able to get that consistent relationship all the way above and below that line. So above that line, we're gonna have to, we have a certain relationship, but then below the line, we have a different relationship. So I'm gonna draw two horizontal rectangles to indicate that, yeah, this right graph is changing. Okay, I'm still gonna indicate that order pair here. Okay, we know that dividing line is right at that intersection or involving that intersection there. Now here's the part that we have to be careful about. If we want to do right minus left, chances are your equation is not going to quite be set up for it. Okay, so you have to kind of get into mindset of, you know, 90% of the time, if you want to do right minus left, you got to work with your equation. The equation has to be in a different form because right now this is set up for top minus bottom. These equations are not set up for right minus left. So let's work with this equation here first. Y equals 2 minus x cubed. How can I get this equation in the proper form? So I need to solve for x, right? So we're gonna get that x cubed on the left side, make it 2 minus y. Okay, so what else can I do to get that x by itself? Cube root, yeah, cube root. Okay, so this is going to be this graph there. Okay, same thing. We need to adjust our tangent equation. How can I rearrange this to get the x by itself? Got to move the tangent, right? What happens if I move the tangent? It becomes what? Inverse, right? Inverse tangent. That allows us to kind of move the trig from one side of the equation to the next. So that x equals inverse tangent of y, that is now the equation that we're going to call this one here. Let me color code it. Make it easier to see. Okay, we're going to depend on two definite integrals. Now there's one more thing missing. We're looking at the y values, right? So from 0 to 1.266, that's pretty good. The other one is 1.266 to this intersecting point. Anyone know what the y value is for that point? Okay, that's the y-intercept, right? The y-intercept is when the x is what? 0. So if I plug 0 for x, I get what? Y equals 2. Yeah, so this order pair is 0, 2. Okay, so we're going to stack these horizontal rectangles from 0 all the way to 2, but we're split up into two separate integrals, right? So we're involving the 0, we're involving the 1.266, and we're involving the 2. Right? We're not touching any of the x's. Everything is in terms of y because we have a different orientation. Okay, so let's set up our area formula. Let's do the bottom region first. So how would you set up bottom region here? Bound is from right minus left. What's the right endpoint of the rectangle touching? Which graph is this? Good, inverse tangent of y, okay. Minus, okay, what's the equation here? What's the equation for the y-axis? Yeah, x equals 0. Okay, so this is the bottom region. Now the upper region, what are the bounds going to be for the upper region? 1.266 to 2. Right minus left. What's the right endpoint touching? Good, cube root 2 minus y minus 0. Okay, we should get the same answer as part A because we're both dealing with region S. Right, just a different orientation. Now, if it was on the AP exam, you obviously would want to choose to do this method over this one, but right now we're practicing and getting used to the different orientations so that when a problem comes where you're forced to have to go through right minus left, you're able to get there. Okay. But right now, we kind of purposely chose problems that that can be done both ways, so we can kind of see that relationship. Okay, enter your calculator. Now, again, your calculator can only handle x's, so don't use y's in your calculator. On paper, you're using y's, but on the calculator, you're using x's. Again, cube root is under math 4. At least on the 84, on the 36 Pro, you're going to have to use the root button. Okay, any trouble here? Any questions? All right, let's go to part B. And now we're going to shift our attention to region R. Okay, let's do region R, top minus bottom. Okay, no questions so far? Everybody good with the calculator? Okay, so let's move over to part B here, region R. You can highlight or you can kind of shade in that region R a bit, very lightly. We'll do top minus bottom first, so we're going to draw vertical rectangles. So I'm going to draw a representative vertical rectangle just to start us off. And we have to ask ourselves, okay, imagine moving that rectangle left and right to either boundary. Is there a consistency? Is the rectangle always touching the same graph throughout my entire interval? It's not, right? Where's the split? Right at that intersection, right? See, the top of the rectangle is all of a sudden switching to a different graph. And if you see a swap, we can't rely on one integral. We need to think that's two separate regions with two separate rules. Otherwise, we're not able to get the full area that we're looking for. So once you identify that, we can identify the boundaries here. We know that we're still involving that intersecting point. So I'm still going to write out the full order pair, even though I'm not going to use the y value, just for reference here. Now, there's one more thing that we need. We know first region is from 0 to 0.902, which is fine. But then the second region is from 0.902 to this x-intercept. So we're going to make the calculator find that x-intercept for us. Okay, but because we're missing this other boundary, we can't just read it from looking at the picture here. So if you go back to your graph, okay, we're going to make the calculator find that intersecting that x-intercept for us. So if we do second trace 0, second trace 0 will help you find that intersection. That's x-intercept for you. Okay, so second trace 0. Left bound, you're just going to use your directional arrow up and you want to make sure that you're on the curve that actually touches the x-intercept. You're going to pick a point relatively close to the x-intercept on the left side of it, hit enter. And then you'll pick a point on the other side of the x-intercept, hit enter again. So now you're basically telling the calculator to look between those 2 points that you gave it. And it should give you 1.259. Sorry, 1.259. Okay, I'm just writing out the full order pair there. That's the x-intercept, 1.259. Okay, you can also find the x-intercept using your scientific probe by setting the 2 minus x cubed equal to 0. Right, you can basically replace the 0 with x and with 0 and solve for x. So we do num solve here, second sign to get to that num solve. And you can do 2 minus x cubed is equal to 0. Start at any point that you want, and then it should find that for you. 1.259. There you go. Any questions finding that x-intercept? Okay. So now let's see if we can set up our 2 integrals, right? We have 2 top minus bottom that we need for the left region and for the right region. So let's do top minus bottom here. We're going to go from 0 to 0.902. Highlight the boundary that we're using. We're only using x values here. Okay, top minus bottom. What's the top of the first rectangle touching? 10x minus 0. Okay, yeah, this is y equals 0 here. And we have a separate region. The second region has a different definition of top minus bottom. What's the top of the second rectangle touching? 2 minus x cubed, yeah. And my bound is from, good. Okay, practice entering into your calculator. Yeah, I honestly think this is the most challenging part of this unit. Just being able to go back and forth between top minus bottom and right minus left, understanding how the boundaries are adjusted, how the equations are adjusted, whether there's a need to split up into separate regions. Because if you feel good about this page, everything that comes after will just be building off of this idea. So if you feel comfortable with this, I honestly think you're not going to have any trouble with the rest of the unit. It's just all building on top of this idea. I mean, we're doing volume, but this is the same foundation. We're just adjusting the equations a little bit, but this is the baseline here. Okay, any questions? Okay, so let's do region R again, but now from a right minus left perspective. Okay. The advantage here is we have a lot of things from above that we can carry down, so it should go faster. No questions so far? So we want to do right minus left, so let's just draw a representative rectangle that's horizontal. And just imagine that rectangle sliding up and down. Is there any sudden change on one side of the rectangle? Or is it consistently touching the same graph as we move up and down? Consistent, right? So there's no need to split up It's not like this one, right? Where as I slide my rectangle above and below, there's a sudden change in the right endpoint of my rectangle. Here, there's no sudden change. It's consistent, touching the same graph all the way through. All we need is one integral. Okay, so I think everything we have already, right? We have the adjusted equation for this curve on the right. We have the equation for the one on the left, right? Right minus left. We can identify our intersection point, but we're only going to use the what? The y value, right? So again, on the 36 Pro, if you want to find that 1.266, you can just plug 0.902 into x of your tangent or x of your 2 minus x cubed, and that 1.266 should appear. Okay, we're stacking these rectangles from bottom to top in terms of y values. So what are my bounds going to be? Yep, 0 to 1.266. Right minus left. Right endpoint is the cube root of 2 minus y. Left endpoint is inverse tangent of y. On paper, you're writing in terms of y, but in the calculator, you're entering in terms of x. We should get the same answer as the previous one because they're both talking about region R. Different orientation, but should be the same area. Okay, any questions? So I wanted to go slow through this page because I feel like if you can see that relationship of top minus bottom or right minus left, and then deciding whether you need to split up into two regions or keep it as the same region, I feel like this is everything. I mean, we're building on top of this with volume, but I think this, if you understand this, it's going to help us a ton for the rest of the unit. Everybody okay? Okay, let's see if we can tackle the next problem. So on page 8, read the problem and see if you can use your calculator to find the bounds and identify whether it's top minus bottom or right minus left. So here we want to choose the easiest path. Okay, so this problem is unique because this problem allows us to do top minus bottom and right minus left interchangeably, but future problems are usually one or the other. Okay, where we're picking because one method is just obviously not going to work. Okay. So, everybody good? All right, page 8. Read the problem and see if you can begin using your calculator. Your graphing calculator can actually, you can actually use the graph, but the scientific calculator can just set equations equal and find those intersecting points. I do want to talk about the graphing calculator for a second. If you want to keep a function for later use, you can just unhighlight the equal sign. If you hit enter at the equal sign, that will just ensure that it's not going to show up on your graph, but you can still have it there in case you want to use it later. So just to kind of give you another thing that could be helpful if you have multiple graphs, but you only want to see one, you don't want to see both, or you don't have to, you have to completely erase it. Okay, you can just tap enter on the equal sign, and if it's highlighted, it's going to show up on the graph. If it's unhighlighted, it's still in the calculator, but it's not going to show up. I like to do zoom box. Draw a box around my region that I care to look a little closer with. Second trace intersect. Now there's two intersections, so you're going to make the calculator look for the one that's closer that you want to target. So you can kind of tell the calculator which one to look for. So basically there's two intersections, but you got to do this twice. Okay, it's not going to find both intersections all at once for you. So we have to kind of tell the calculator, okay, choose the closest point between these two curves, 0.446, and I got to do it again, and then pick a point that's closer to the other intersection that I want to find. Now I'm going to pick a point close to that other intersection. Again, make sure that you never put your cursor on the intersection, because then the calculator will get confused. It doesn't know what you want it to do. So pick points close to it, and then make the calculator find it for you. Okay, 1.554. Okay, should be a pretty straightforward top minus bottom setup. On the 36 Pro, if you want to find those intersecting points, you can do numsolve. And then you will say e to the 2x minus x squared equals to 2. Hit enter. Now, I think in this case, you do want to give it a starting point, okay? Because it's not going to find both intersection points for you. I'm going to say start at 0. If I start at 0, it's going to find the closest one towards 0. Which is 0.446. If I want to find the other one, you can go to solve again, but then make the calculator start at a different point. So make it start on the other side. You can tell that it's closer to 2. So make it start at 2. And that way, it'll find the closest point, closest intersection to that point. There it is, 1.554. Okay, so let's set up our definite integral. Top minus bottom. The top is the curve. The bottom is the y equals 2, and then left to right, 0.446 to 1.554. Okay, let's see if we can explore part B. Part B says find the area of S. Find the area of S. So there's two ways that we can go about doing it. We can think of it as, okay, 3 regions, right? I can do this region, and this region, and add them all together. I think there's another way, though, that may be a little cleaner than that. And what if we do it this way? This is 1. What if we find this entire region first? And then just do what? Yeah, and then just subtract region R. So that feels a little bit cleaner because then you don't have to split up into 3 separate regions. So the idea is that you find the integral of r plus s, right? You find this full entire region, and then you can just subtract out that r that we have from above, and then we can isolate that s. So to find that full region, we do need to basically ignore that 2 for now, and just find that intersection between the curve and y equals 1. It does land at a nice number, though, right at 2. Top minus bottom is going to be the curve minus 1. So we're just finding that full region first, ignoring that little region for now. And then we can subtract out that region that we found from part A. Okay, I delayed all the homework assignments by 1 day, so tomorrow I'll check Monday's homework, and we'll just shift all these homeworks 1 day over. Yeah. All right. They're all 10. Yeah. We need negative.
I don't know my I like happened to. I thought one was on the soccer team, but then both were, so I should have been soccer practice, and I waited for them to get out. And then I got in a car chase, and then I went to one of the classes. I know one of them. He really did probably go back.
So first curve, second curve, highlight black. Doesn't matter. As long as you're going right, as long as you're close, it knows to look right. Hit enter. Again, it's on I see that.